Good day, everyone, and thanks for your time to attend today. We're talking about the project to update the 2014 solar PV assessment tool, and we migrated that from a downloadable Excel file to a more user-friendly online platform. And one of the innovations that we aimed to bring in was to normalise around business metrics important for the broiler industry, designing and trying to automate the design of those PV solar arrays. So the metric that's used quite commonly is number of sheds, and then you can modify that to surface area with assumed stocking densities to then arrive at a estimated power requirement for given geographic areas. We've made quite a number of allowances in that design of these small scale credits for systems up to 99 kilowatts, and then over that flips into large scale. Certainly in the current environment, the small scale credits are able to be received up front and at a higher dollar value. So there's an optimal size there up to 99. We brought in batteries, and then we started looking at thermal energy options that show some strong promise in terms of short payback periods. So solar thermal with dry heating systems to replace LPG and natural gas systems, and running some numbers on those. So this is the portal, this is the landing page. It's up online now, free for anyone in the world to use, but you do need to create a username and a password to log in, and that'll take you through to the calculator region. If you prefer to use your smartphone, or if you have your smartphone readily available, take a photo of the QR code and that'll take you directly to the website, or you can put the website into your favorite web browser. I've only got about 10 minutes today, so we won't spend time going online to register, but in your own time, do get on and have a look around at some of the calculators there. So what we've got is a straight up PV solar, and then a PV solar plus battery, the solar thermal system. So good examples of these are those black plate collectors, and then also vacuum tube systems. And for these more commercially scaled systems, you're expecting temperatures to reach towards that 80 degrees Celsius. So the temperatures which can be quite useful for dry shed heating. And another one of high interest to the industry was making those diesel generators work a bit harder, be those emergency generators or backup generators, to help drive down the kVA or maximum energy use within a particular month. And I'll talk about how bills are set up on this next slide here, just so that you can understand the approach that's been taken. When you look at your electricity bill, there's two main contributors to the final dollar per month that's being paid. It's the kilowatt hours. So this is the volume charge, or how much you use. So a kilowatt rated pump running for 1 hour is 1 kilowatt hour. And the second big one is the kVA, or the capacity charge. You might see these as the NUOS or the GEOS charges, also called network charges. And network charges have a large kVA component, and they also have a kilowatt hour component. The retail charge is normally a kilowatt hour. Environmental charges are often based on a kilowatt hour usage as well. So if this is a NIMI meter or national meter identification, custody meter, which is what you get charged on, the surface area under that blue curve is the kilowatt hour usage, whilst these spikes represent that maximum kVA. And so as you can see here, there's this one single large spike. And so within that month, that particular energy user would have been charged at that spike. In this month, it would have been this spike here. The analogy for thermal heating is that your gigajoule bill or cubic meter or litre of LPG bill is on how much you use. And then the amount that you use is wrapped up into the capital cost of the size of the equipment, or it could be the diameter of the natural gas pipe, or the having larger LPG tanks to give you that larger availability of fuel. If you have a look at a typical sort of industrial commercial bill, quite often 40–50% will be those kilowatt hour charges, and about half will be the balance. So these network charges used to be a relatively small percentage, but it's growing and growing. And where you do see EMO stating there's a lot of energy out there and everyone will have plenty of energy and the wholesale price is dropping, that will be very good for bills. But this network charge has continued upward pressure to keep the poles and wires energised. Environmental charges tend to be reasonably stable at the moment. We don't know what will happen after 2030, but through to 2030 should be reasonably predictable. And then there are these other daily metering charges as well. So armed with that information, with those two really critical numbers on kilowatt hour and kVA charges, we then built up the bill. And as mentioned, a really critical business metric in particular to determine energy usage is the number of sheds, and then obviously the size of the sheds as well will then define energy load within those. It's not a least squared regression one correlation. It's not an absolutely perfect correlation, but there is a sufficiently strong correlation that the error is quite small to correlate size of sheds back to energy load. So it was the best metric for rapidly determining the amount of energy that a particular operation would need based on some simple input numbers. You can nominate the percentage of energy that you'd like to offset, and then a geographic point as well, which will define the solar resource available. So all that input data is dragged through into the algorithm to determine the size of the array, the percentage of roof area covered. Obviously, orientation is another very important element. If your building is north-south oriented, then up to 50% you should get quite high efficiency. If it's east-west, don't run away in fear, but you will have some efficiency losses there. So you'll probably need a more accurate or more detailed model. You can nominate your power volume price. There are default numbers entered in here, so you can get in and have a look at an example without changing any of these numbers. And every jurisdiction, every state, every retailer does have slightly different ways of putting forward these power demand prices. So we've tried to simplify it into a single number of $1 per kVA per day or $1 per kilowatt hour per day. A lot of bills will have that $1 per kVA per month, so you'll just need to calculate out for what that is for a day. So that's the input data. You can leave everything as it is or change whatever you want. Click return, and then you'll get a neat report into your inbox. Here's an example that I just ran on offsetting natural gas with solar thermal. And I mean, the really critical stuff here is what's your CapEx, so that's your system cost, how much you're saving, and an approximate simple payback period. You will be able to get more detailed analyses if you go to the market, or for detailed site-specific modelling. And as per any good procurement approach, get 3 complying submissions from the market before making a final decision. But certainly these tools give you a good guide on where some opportunities might lie. Here's an example of a solar thermal system. You'll normally have a heat storage system or a tank with a pump, heat exchanger, variable speed drive to recover that heat as required. There's some advantages there around using one of these closed systems to provide dry heat into a shed. There are some fancy finned heat exchangers that I've seen coming out of Europe, but an appropriately sized copper pipe or piping might be able to provide the heat transfer that you need within your particular shed. So there are some lower cost heat exchange opportunities for within sheds. The dry head has been quite popular in New Zealand, and we did hear about moisture and humidity a little bit earlier. In those colder, wetter climates, dry heat is certainly becoming quite popular. So we've accounted for that within the solar thermal. And then, as mentioned, there's also the diesel generator KVA offset, where it's not a renewable energy solution, but it's a electricity cost reduction solution that's available. So when we look at the big outcomes that we're trying to get from this, provide some rapid ideas around reducing power costs, obviously reducing the thermal energy costs as well, with the greatest opportunity being around LPG. That has come off the boil from low $30 odd per gigajoule levels down to, I'm seeing prices in regional areas about $22 per gigajoule, but it is still a very expensive source of energy. Natural gas has also come off the boil from spikes in the $20 odd per gigajoule, now down to mid-teens. Seems to be reasonably common for commercial industrial pricing. However, it is still at a much higher price compared to solar thermal, which might be over the life of the plant at around that $2 to $3 per gigajoule. So you can see there's some good opportunities to reduce heating costs. Improving air quality. If you're combusting a fossil fuel and putting that flue gas straight into a shed, there is a high moisture cost. And even though it's a lot better than other dirtier sources of fossil fuel, there is some very interesting work being done by QUT on very small nanoparticles, which may not be visible to the eye, but those carbon-based molecules and soot particles are still there. And obviously, keeping that water moisture and flue gas out will help to reduce moisture and provides dry heating. Improving environmental outcomes, social license to operate. There's not a direct price on carbon emissions at the moment, but certainly I would anticipate any heating system installed today with a 15, 20, 25-year life would probably be operating in the future under a carbon constrained world, that is where there is a carbon price on emissions. So it is worthwhile keeping that in mind, potential changes that could occur, especially after 2030. Decreasing reliance on fuels and fuel delivery. We've seen with COVID supply chain disruptions, there is only a couple of weeks worth of fuel storage within Australia. So providing greater opportunities for domestic or local heat usage. And certainly within that backup diesel analysis, there are opportunities at reasonable costs to get combined PV solar backup diesel synchronizing energy management systems, so that if the grid goes down for whatever reason, you've got your diesel generator, and then you can also make use of your PV solar energy as well. And then reduction in those direct emission scope 1 emissions and indirect electricity emissions scope 2 emissions. Thanks for listening. That was a very quick run through on the tool, but get online, have a look at the portal, run a few scenarios, and certainly email through any questions that you might have.